How's it going?
Good. Oh, Grace got food. Like Michael's gonna steal some of Grace's stuff.
I would never do that. I would never do it at Brad Pitt.
Questions about anything before we get going?
No. When are our tests?
2 weeks, yeah.
Before.
It's before. It's the week before, actually.
That's how I look at my holiday breaks.
I like that.
Well, we don't have class on the 15th because I'm gonna be out of town, which is why it's not on Thursday.
Is it next week on class on Friday?
15th of Friday.
The 15th of Friday, yes, we do not have class on the 15th. So I said we don't have it on the Thursday because I won't be in town on Thursday.
Is it the week?
That's why it's the next week.
Oh, so it's the week before Thanksgiving.
Correct, it's the Tuesday, yes, it's the Tuesday before the Tuesday before Thanksgiving.
I mean.
Well, that's good because people know that it's day of Thanksgiving.
When's the
That's why that's why it's not on a Thursday this time.
I like this because it's like calc, and then I think I have physics, and after that I have physics.
All right, let's see if we can do this problem. We talked about doing probabilities last time. So, zoom in on this a little bit here. Should have problems now. I gave you packets, right? So this one should be... not that one. So if you flip back to where it starts, it says problem set. Okay, so the one that says 11 exercises for 11. Okay, if you flip in to, I think it's the 4th page where it starts to say problem set 8 instead. It's number 3. So the 4th page of the packet that starts with exercises for 11, it starts where it starts to say problem set 8, it's number 3. In my theory of interest class, we call these Franken packets, right? Yeah, Haley calls them Franken packets.
That was like a holiday joke.
Yeah. I like it.
And just work with it.
All right.
We were talking about that other thing this morning.
So we started talking about doing joint density functions last time and how to calculate probabilities. Here's an example of a continuous one. So again, we have a region that's not rectangular here. So if I look at what the region has to look like, if I draw it, we know the x's go from 0 to 2, and our y's, the boundary line is y equals 2x. So our y's also go from 0 to 2, and then my boundary line will be there. And we know the y is less than or equal to the 2x and above the x-axis. So that triangle is the support here. I guess technically it's joint support. Everybody see that for the region? The reason why this is important is because when we're calculating probabilities, we're going to have to do integrals to calculate the probabilities. But our integrals here are going to end up being double integrals because we have 2 variables. All right? So for this one, we want x to be greater than 1. So here's where x equals 1 is, right? So this is the region that we want to integrate over. All right, so the probability here that x, bless you, is greater than 1, we're going to set up a double integral of our PDF, and then I'll have dy and dx at the end here. Do you want to integrate with respect to x first or integrate with respect to y first? Okay, if I integrate with respect to y first, means you would hold x constant, right? So we do dy and then dx. What do your y's run through? 0 to 2 minus x. And then your x's run from 1 to 2. Are there questions on setting that up? Because once we set it up, the process is exactly the same, right? Honestly, the hardest part in these problems, besides remembering how to integrate, is getting your double integral set up correctly. Yeah, Marshall?
Is setting up these double integrals, are they always going to be pretty straightforward like this, or are there going to be some harder ones that we see later?
It should be pretty straightforward, or you might see that it's easier to do the complement, so you do 1 minus the double integral. You want to try to set up, for example, if I wanted, well, this one's not a good example. So if I wanted this probability, I could do 1 minus this probability, for example. I mean, that one's not much harder to set up that way, but I'm just saying, you could have a scenario where you'll do subtract off from 1 and do the complement instead.
Right.
Or it might be a little easier to set up. No, they should be pretty straightforward to set up.
So if we anti-differentiate this with respect to y, all we're going to get is a y and then plug in our endpoints, right? Right? Our endpoints are 0 and 2 minus x. So if I put that in and distribute, we should get what? 1.5x minus 0.75x squared? If I do all that at once? We'll have 0.75x times 2 minus x. So then we get 0.75x squared and a 0.25x cubed, evaluated from 1 to 2. You get, what, 1 minus 0.5, so you get 0.5? If I did my numbers right. Yeah, Grace.
Why did we have to do the integral? Why couldn't we just do it rapidly?
Because it's not uniform. That area is not a half of the whole area. That area is not a half. That area is a quarter of the total. Right? Right? This area is only a quarter of the whole thing, I think. Right? Because this has an area of a half and this has an area of 2, so it's only a quarter of the whole thing. So I can't do it graphically.
Okay.
If this were a constant, I could have done it graphically. But we've got a weighting function on here, right? It's weighting the x coordinates. The bigger the x coordinate gets, the more likely it is. That's why we can't do it that way. That's a good thought, though, because if you've got uniform distributions, thinking about it in terms of area will save time. If you know that if it's a uniform distribution, if it's constant, then you can do areas that way. But this one didn't. This one had an x in it. The best I could do is what I did with the y, right? It's constant as far as y goes, so I know the integral is just going to be the difference of the coordinates. Just 2 minus x. This one okay? We're so quiet. Usually it's rambunctious. Of course, our freshmen weren't rambunctious this morning either.
It is Monday, I know, but usually my freshmen are rambunctious no matter what day it is.
Are you teaching ethics in that? What are you teaching your freshmen?
Misuses of data.
What's that?
What kind of stuff are they learning?
We're reading Weapons of Math Destruction right now.
I read that last fall.
Yeah.
No, last spring.
Yeah, fun. Is that Dr. Olson's class? Yeah.
Dr. Olson's ours.
Yeah.
Math more real.
So you learn about, they're using online ads to target people in low-income areas to go pay for for-profit education, and then they can't pay for it and don't get through education, for example. The article, let's see, what else is there?
Did you check out that website?
Which website?
The one RJ we use with all like the misuse.
Oh, the graphs. Yeah, I've seen that one. Yeah. All right. So here's another one where we're asked to find some probability. They give us the joint density function again. I'm not worried about all the words. It asks, what's the probability that the total is at least 1? So we know we're going to have to do a double integral to calculate probability, right? Well, we've got joint density functions. If we're going to do probabilities, they're going to be defined in terms of these double integrals as far as continuous distributions go, pardon me. How would I represent the total loss in this case? If x and y are both representing losses, what would be the total loss? How would we represent that? X plus y, it'd be greater than, yeah, okay. 1, good. And we want the probability, right?
We're still on problems at 8.
Yeah. We agree with the setup here? X plus y gives us the total. We wanted at least 1. Okay. All right, so let's think about the picture again. Because again, most of these problems are, can you set up the double integral? X goes from 0 to 1, y goes from 1 to 2, or 0 to 2, sorry. And we want x plus y greater than 1, or y is greater than 1 minus x, right? So that line would be this way, and we would want above, right? Because that's y is greater than 1 minus x. We agree? Are we okay with how I set that up? Haley's not, but Haley didn't count. We already established that Haley's a snot. Yeah, maybe. What's that? What'd you say?
Calling that on 2 videos?
Yeah, I caught it on 2 videos now. Yeah, it made
It's
it.
because you're adding the losses.
Yeah, because it says the probability the total loss is, right?
Because x is a loss and y is also a loss.
Yeah, because x is a loss and y is a loss, right?
Okay, so exactly.
Mhm.
Can you explain how you do
This part? Okay, so this part, if I just solve this for y, that's y is greater than or equal to 1 minus x.
Oh, and that's it.
And that's that line. Yeah, and then I just shaded above. Yeah. So as a double integral then, I know I'm going to double integrate the joint PDF, that's a y. Do you want to integrate with respect to x first or with respect to y first? Yeah, I probably want to do y. If I do with respect to x first, I've got to break it up into 2 integrals, don't I? Right? If I do it with respect to x first and hold y constant, I've got different left bounding curves. Right? So I really don't want to do it that way. Now, you could, what Marshall was talking about before, I could go down here and calculate this probability, where I just shaded in at the bottom, and then do 1 minus, if it's easier to set up that way. Either way, you could do that. You could do it either way. It doesn't matter. I mean, this one's not hard to set up doing with respect to y first, right? Because if I do it with respect to y first, what are your bounding curves? 1 minus x to 2, and your x's go from 0 to 1. Still looks like an x to me. But, oops, didn't mean to erase the whole fraction bar. And then it would just be a matter of getting your integral done. Not necessarily pretty, but it is what it is. It's not a hard integral to take, right? Can I do the integral? Sure. Pull the 1/4 out, just so I don't have to deal with it. I'm integrating with respect to y, so we'll get 2xy plus 2y minus y squared over 2.
So let's see, we put in 2, we get 4x plus 4 minus 2. Put in 1 minus x, we'll get, I'm going to distribute when I can here. If I put in 1 minus x, we'll get 2x minus 2x squared plus 2 minus 2x, and then minus 1/2 plus x minus 1/2 x squared. Ooh, that's long.
I know I did 2 steps at once, but I was just trying to make it a little bit faster. All I'm doing at this stage is just plugging in the endpoints, right? Hopefully correctly. When I'm trying to do things, when I'm trying to do it, doing a couple of steps at once, sometimes it makes it a little bit nastier. But all I do is put in the 1 minus x here, here, and here, and distribute, right? So I should get 2x minus 2x squared for that one, 2 minus 2x for that one. I gotta FOIL this on top, you'll get a 1 minus 2x plus 2x squared, or excuse me, 1 minus 2x plus x squared, and then distribute the minus 1/2 through. So I think I did all that right.
And now, if I simplify before I integrate again, okay, let's see. Let's take care of the constants first. 4 minus 2 is 0, minus a minus 1/2. So I've got plus 1/2. I took care of that, and that. Take care of the x's. 4x minus 2x plus 2x, so I'm still at 4x, minus x. So I've got plus 3x. And then I've got plus what looks like 5/2 x squared. Again, presumes I've done all my algebra steps right. Which, no, it's okay so far. So if I anti-differentiate that, we should get a 1/2 x, a 3/2 x squared, and a 5/6 x cubed. When I put in 0, I'm definitely going to get 0. When we put in 1, we should get what? 17/6 on the inside, so you get 17/24. Hopefully that was one of the answers.
Yes.
Yep. Was it D?
Yes.
Okay.
Well, it was just a polynomial, so the integral wasn't too bad. A little longer than probably necessary, but does the idea make sense what we're doing? You okay with that?
All right. We can do the same things that we've done before with distributions. Let's see if I can pull out another one here. Nope, don't want to do that one yet. All right, I'll do this one. That's fine. Let's look at, this is same, that problem set 8 still. This should be number 7. This is a discrete PMF, probability mass function. So the car dealership doesn't sell a lot of cars a particular day. They don't sell any, or they sell one, or they sell two. And if they sell a car, then they do the hard sale and try to sell an extended warranty as well. Okay.
So certainly you can't sell more extended warranties than you can sell cars. So the X has to be at least as big as the Y, right? You have to sell a car before you can sell an extended warranty. So that's why we see a probability that X can be 0, 0, or X can be 0, Y can be 0. We see one for X is 1, Y is 0. We don't see the X is 0, Y is 1. Right? If I don't sell a car, I can't sell a warranty. That makes sense? That's why those are like that. All right, so the problem now asks us to find the variance of X. Well, we know how to find variances and means back for variables, for distributions with just one random variable. It's the same concept here if I want to find means and variances for a variable for two random variables. We'll still do the same thing. So the mean of X will still be expected value of X. Same idea. But instead of doing a single sum, we'll do a double sum of X times the PMF. It's still a weighted average, same idea that we had before. We'll just do a double sum in this case because I've got to sum up over all the X's and all the Y's. But it's the same concept, right? And in this case, there's only 6 possibilities anyway. So if we write out this double sum, if X is 0, what's the probability that X is 0? Well, I could be this 1/6 here, right? And that's it, isn't it? Right? This is X is 0. This is the probability that X is 0, right? How can X be 1? Well, there's a couple of ways, right? This one or this one? And then for 2, it's the rest of them. I did it a little bit differently, thought of it a little bit differently. I could have written out each individual thing, right? If I wrote each individual thing out, I would do this probability times 0, this probability times 1, this probability times 1, this probability times 2, this probability times 2, this probability times 2, right? Those are the X values. I just factored them out. Or thought the other way, I thought of it in terms of just a single variable, right? Probability that X is 0 is just 1/6. Probability that X is 1 is, well, it's either a 12th or a 6th, right? So I added it together. Probability that X is 2, it's one of those 3 possibilities. So if we go through and add this up then, this first part is a quarter, right? 1/6 and a 12th is a quarter. You get 3/12. Over here we've got a third and a 6th is a half. Plus another 12th is 7/12. 7/6 and a quarter. So a quarter is 3/12. We just said that. And then 14, so 17/12. If I did my arithmetic right. Fourteen twelves and 3/12 is 17/12. So if I did my arithmetic right, to begin with, I got to put that number right. Good, thanks, Alex. Appreciate that. Awesome. Is that computation okay for finding expected value of X? You can do the expected value of Y the exact same way. Good question, Katie.
I was just so there. It's really only one sum. I mean, it's 2 sums, but where's the double sum? I get that it's X just because it's.
So I didn't write the limits on there. So your X's go from 0 to 2, and your Y's go from 0 up to X. So when X is 0, you would just have one term. When X is 1, you have 2 terms. When X is 2, you have 3 terms. So it would look like that. I just didn't write the actual summation out. Yeah.
So 17/12 is the answer?
Nope.
Okay.
That's the mean.
So, yeah, but that's...
Yeah. I'm not done yet. But if I wanted to do the mean for y, I would do it the same way. Right? And there was nothing special about sums. I could have done integrals as well, right? It's going to be continuous. I would do it the same way. Okay? Now, we need variance, though. For variance, I need expected value of x squared along with it, right? So how is this going to change for expected value of x squared? What's going to change? You know, the x's will just be squared, right? Right? So I would have 0 squared times a sixth, 1 squared times a 12th plus a sixth, 2 squared times a 12th plus a third plus a sixth. This was 7 twelfths to begin with. So this would be 28 twelfths and 3 twelfths. Ooh. This was 7 twelfths times 4 is 28 twelfths plus 3 should be 31 over 12. So then if we want the variance for x, how do we find the variance? Same way we found the other variance, right? Expected value of x squared minus expected value of x quantity squared. 31 times 12 is 310 plus 62. So 372 and 280, good Lord, that's too many numbers. 372 and 289. So 83 over 144. That hurt. That one hurt. So, of course, the answers and the problem were given to us in decimals. Well, 0.83 is 5.6, so it can't be that. It must be the 0.58.
Yeah.
Well, 72 over 144 would be a half, so it's a little bit bigger than a half. And certainly not as big as 5.6, which is what the 0.83 would be. Yeah, morning.
Can you explain the notation for the double sum again? Like how, because like I understand how we wrote it out above, but like why is the y up or down x?
Because remember, in this particular, it wouldn't necessarily be all the time. That's context of the problem here. The y is representing the number of extended warranties sold for the cars. Well, I can't sell more extended warranties than I sell cars. So the upper limit for this particular sum has to be x, because I can't do, because x is the number of cars sold. In general, this might be something different. It was just x in this context of this problem, because if x is the number of cars sold, then the y can't be bigger than the x. So the y is where it tops, the x is where it tops out.
Okay. So is there more computations that we did that I'm just not seeing for the double sum? Or is it just?
So again, when we put in 0 for x, there's only one term here. Y goes from 0 to 0, that's this one.
Okay, I get it now.
Yep, and when x is 1, I've got two terms, that's this one.
It clicked.
Yep, and when I put in 2, that's those three. So when x is 1, there's one term. When x is 2, there's, excuse me. When x is 0, there's one term. When x is 1, there's two terms. When x is 2, there's three terms. That's how that sum's working. It's not as important to understand that particular notation as it is to make sure we get all the appropriate sums and products in there. The notation's more important when you do the integrals because it actually matters what the bounds are when you're doing the double integral. That's why I didn't write them to begin with. That's okay? Since we had so much fun with that one, let's do another one. Really did not want me to get that little anchor thing off of there. All right, number 5.
I know, there's a lot of words. Okay. The words aren't as important as the actual setup of the problem. All right, so let's ignore the words. Okay. So let's just look at the set of the problem. The joint density function of T1 and T2 is constant over that region. Start there. Okay. Because that's an important piece of the problem, right? It doesn't actually give us the formula for the joint density function. It just says that it's constant, correct? Okay. So if this is my T1 axis, this is my T2 axis, I go 6, 6 here, right? But what else do we know? The sum of the two is less than 10, right? So here's, this one's going to look a little bit weird. So let me draw in a couple of helping lines here. This would be T2 equals 6. Here would be T1 equals 6, right? But it's not that whole rectangle, right? In particular, if I put in 6, 6, I get bigger than 10, right? Okay. So this top corner of this rectangle is going to get chopped off, top right corner. If T1 is 4, the biggest that T2 could be is 6, right? And then similarly this way, there must be a 4 here. So I've got this line coming in this way. So this is the region I'm talking about. And not, just put an X up here just so you know it's not this part. Everybody see where I came up with that? So T1, 4, T2, 6 gives me 10, and then vice versa. And then I just connect the dots, because it has to be that same line. Okay. All right, so that's the reason we're talking about, a little bit weird. I agree. Okay? But it says that what the problem says that we should be able to find the joint density function pretty easily. Because it says the joint density function is constant. Right? If we do the double integral over the entire region of the joint density function, what do we have to get? We have to get 1, right? Now, if it's a constant, say I just used 1 to start with. If I were to integrate 1 over this entire region, what quantity would I get? Not number, what quantity? What physical quantity would I get? If I just took 1 and did the double integral over the region, what physical quantity would I get for the region? If I integrated 1, what physical quantity would I get? What of the entire, the blank of the entire region? There's the word, it's the area, right? If I integrate 1 over this region, I get its area. Right? Okay. So can I calculate what the area of this region is? Yeah, it's actually pretty easy, right? If I did the whole rectangle, it would be 36. And if I do this little triangle, it's just 2, isn't it? Because it's 2 by 2 and then half of that, right? So this region must be 34. Good. So our joint, so the area is 34, right? So what does the joint density function have to be to make sure that when we do the double integral, we get 1? It has to be 1/34. Yeah, good. So the area of this region, we know, so just to write this down, if I take the double integral, I don't know why I'm still in red, but that's okay. If I take the double integral of a region over the area, over just dA of a constant 1, this gives me the area of the region. That's just true in general. Right? Calc 2, 3-ish idea. Yes? If you paid attention in Calc 2 or 3, it's the Calc 2 or 3 idea, right? Okay? Well, it's the same concept, isn't it? If I do an integral from a to b of just dx, what do we get? I get b minus a, which is the length of the interval, right? What's the two-dimensional analog of length? Area. What's the three-dimensional analog of area? Volume. So if you do, I know in Calc 3, if you're doing triple integrals, if you triple integrate 1 over a solid, you'll get the volume of the solid. Same idea. Okay. So we're not going to do 3. We'll handle it. We'll stay at 2. That's good with everybody. Okay. All right. So we get the area of the region, but when I do but we also know that when we do the double integral over the region of a joint density function, I'm going to write f of x, y, we're supposed to get 1, right? Right? So to make these two mesh with each other, I better make this thing 1 over the area, right? Right? Because if this is a well, remember this is supposed to be a constant, correct? In this particular problem. So let me write it, let me make sure. If it's going to be a constant, right? Because if this is a constant, what could I do with it? Put it out in front, right? So you'd have that constant times the area has to be 1. So it has to be 1 over the area. Everybody's looking at me like I'm nuts, right? If this is a constant, I mean, I am, but not for this. I'm right about this, right? If this is a constant, I can take it and move it out front, right?
Yes.
If I double integrate 1, I get the area.
Yes.
So to make that constant times the area to be 1, I better have that constant be 1 over the area. All right? Okay. All right. Shoo. All right. So in this particular case, then, your joint density function for T1 and T2 better be 1 over 34.
And just to explicitly say, there's no variable just because it's the constant. It literally says that.
It literally says it's a constant. Yep, that's right. Yep. It's telling us that it's a constant, so there's no variable. It might also tell you it's uniform. So it's another way to say that it would be constant. It would be tell you it's uniform over the region. Okay. All right, so now we have the joint density function. Now it's telling us to find the expected value of T1 plus T2. How do you think we would find that? Okay, definitely want to do a double integral over the region. Okay. What's going to be inside here? It's going to be a 1/34th. Yeah, it's going to be the times the T1 plus the T2. Good. Remember, whatever's in here is what goes here. Now this one, as far as the integral goes, kind of stinks. Well, it does. I can't help it. Why does it kind of stink? Look at the region. I got to split it into 2 pieces, no matter how I do it, right? I know it stinks. I don't like it either. But I have to, and the reason why I have to is because I actually have to do the integral. Because it's not just a constant. I can't play the area game. Right? Because I'm multiplying by a T1 and a T2. Right? And if I go left to right, I change bounding curve on top. If I go bottom to top, I change bounding curve on right. So either way, I have to do two integrals. That would be a good way to try to do the probability. Unfortunately, it's not a probability of an expected value, so I got that extra t floating in there. That's what you're right. If I could do the complement, that would be fantastic if I could, but it doesn't work in this case. A, I have to go over the whole region, and B, I got a t floating around in there. Because we were doing the expected value with because we're not doing the probability. Okay. All right, so I'm not going to go through the whole integral because I'm not going to go through the whole integral. If I say we hold x constant, integrate with respect to y first, what does your first integral look like? What do your y's go through? And then your x's go from 0 to 4, right? So your first integral would be 0 to 4 for the x's, 0 to 6's for the y's, or at t1 and t2. Yeah, write it this way. And if you want to change it to x's and y's in your notes, that's fine. I'm just being consistent with the problem. Does everybody see that first part? It's just that rectangle. dt2, dt1, because the problem said it was the variables were t1 and t2. Like I said, if you want to do x's and y's in your notes, feel free. They're your notes. How am I going to know the difference? All right, what about the second part? Over here. This was what was this line again?
T1 plus T2 is plus.
So the line is actually equal to 10, right? So your T2 would be 10 minus T1, or y equals 10 minus x. So what do your y's go from? Good. So 0 to 10 minus T1. What do your T1s go through for that piece? 4 to 6. Good. And then just, you would need to go through your integral. Do you have a question, Megan? Yeah, it's a 0 log. Yes. Sorry. You don't like T1 and T2? Is that what you're saying? I didn't like it either. I was just being consistent with the problem.
Mostly because my T's look like pluses too, so I'm like.
This is why I have the hooks on mine.
I do have the hooks on mine.
And they still look like a plus?
When I'm writing really small, I can't tell.
Gotcha.
It's big right now. So.
Is that one okay? Yeah, this idea makes sense. I know the region was goofy, but the idea makes sense?
Yeah.
Yeah? All right, one more concept, and we'll do more of these on Wednesday. Let's talk about what we mean by the marginal density function. So this is, should be same problem set 8, but it's exercise 12 on that. Oops. Oh, that's right. That's not what to do. Okay. All right. So this gives you a joint density function and asks for the marginal density function for y. So your joint density function, again, gives you probabilities that are associated with regions in terms of x's and y's, but you should also be able to recover PDFs for x and for y from the joint distribution. Meaning that x is a random variable, it should have a PDF. Y is also a random variable, it should have a PDF associated with it. That's what the marginal density functions mean. Okay? The marginal density function for y is just the PDF of y. That's all it means. It just means that we have to recover it from the joint density function. Okay? All right, so let's see how we do that in this case. It's actually not that bad. It sounds more complicated than it is. Okay? All right, so this says that this is true for all y's that are between x squared and x. Well, here's y equals x squared, right? Here's y equals x, kind of, a little wavy. Where do those cross each other? 0 and 1, right? So your x values go from 0 to 1, don't they? And so do your y values in particular, okay? This is the region. All right, so to find the marginal, which the problem is calling this g, right? So to find the marginal density function for y, we're going to take just the single integral of the PDF over all the x's. Okay? Now, you have to be careful. This is like you're doing the inner part of a double integral. Okay? So it's like you're holding the y constant and changing the x. Okay? Does that make sense? Now, notice that if I hold my y constant but move my y, my x bounds change, don't they? I can't just do 0 to 1, correct? This is why I said it's like the inside of your double integral. These bounds may very well be in terms of y's. Okay? Can't be in terms of x because we're integrating with respect to x. Once you integrate with respect to a variable, it's gone, right? You learn that when you do double integrals and triple integrals, correct? When you integrate a variable, that variable goes away. Right? Okay? So this, again, was y equals x. This is y equals x squared, but we need x bounds, not y bounds, right? Because we're going to hold our y constant. We're going this direction. So in terms of x is in terms of y, what's your lowest x bound that you have? You have y is the lowest one, right? What's the biggest y? What's the biggest x bound? Square root of y, right? We agree? Okay. Now we can do our antiderivative. That's just 15y times x, right? We agree? Because it's just a constant as far as the x is concerned. We get 15y times root y minus y. Which looks like one of these. It's this one. Well, it's one of these two. It's D or E, isn't it? If I factor out a y to the 1/2, it's either D or E. Which one does it have to be, by the way? It has to be E. At this point, we actually need actual bounds for y, right? Numbers. I told you that when we do the marginal density function, we do the integration, that's like it's the inside double integral. That the second piece would be like it's the outside double integral. Those bounds have to be constant, right? So it has to be E and not D. Okay? What's E trying to trick you, or D trying to trick you with? It's trying to trick you with the bounds that were given in the problem, right? But these bounds for the marginal always have to be the constant. We'll do more of these marginals next time, so you're going to get the hang of doing those. But again, don't get confused by the words. The marginal just means you're finding the PDF. Okay. And again, basically, you're going to do half of a double integral. You're going to do the inside. Have a good one. We'll see you Wednesday.